discuss the chain rule for derivatives. So the chain rule for derivatives is used when we have a composition of two functions. As a reminder, composition is when I have one function embedded inside of another function. So here down below I have f of g of x. G of x would be our inside function that is the input to f of x. And we can take the derivative of a composition of two differentiable functions by first starting by taking the derivative of the outside function. So our outside function here would be f. So since I don't know what f is, I can represent its derivative by f prime. So I'd get the derivative of f, which would be f prime. I would then keep the inside function the same. So g of x is the input here. It's staying exactly the same. Notice I'm not calling it g prime because it is still the original function, g of x. Times, though, then the derivative of the inside. Now I get to take the derivative of g of x, so I'm going to represent that by saying g prime of x. And this is multiplied outside the composition. Now down below I have this in words for us, so we start by taking the derivative of the outside function, so this would be our f prime. We keep the inside function the same, this would be the g, then times the derivative of the inside function, that g prime there. And this chain rule comes up a lot, especially as we start to talk about derivatives of trig functions, exponentials, or logs, because all of those are compositions of one of those functions with whatever the input to the trig function, the exponential, or the log would be. So let's start looking at our first example here. Here we have the function y equals 5x squared minus 9x plus 2. All of that is being raised to the 8th power, and we want to find the derivative, or dy over dx. So one option we would have would be to actually algebraically multiply all of this out, but multiplying out 8 of these together would take a very long time to do, which is why the chain rule comes in handy as kind of a shortcut way to avoid doing all that algebra and just going straight to the derivative. So in this setup here, our outside function is the 8th power, because all of the quadratic inside is being raised to the 8th power, and then our inside function here would be the 5x squared minus 9x plus 2. So when we take the derivative using the chain rule here, let's start by labeling what we're going to find. So I'm finding dy over dx, or our derivative. I'm going to start by taking the derivative of the outside function. Our outside function is this 8th power. Now to take the derivative of something to the 8th power, we'd bring down the exponent of 8 using the power rule, and our new exponent would be all of that, whatever the base is, to the 7th power. Now in the chain rule, our input here is the 5x squared minus 9x plus 2. So far I've done part of the chain rule here. I took the derivative of the outside function, so using the power rule, the 8 came down, and I'm now to the 7th power. I've also kept the inside function here, the quadratic, the same, times I now want to take the derivative of the inside function. Now the derivative of 5x squared would give us 10x using the power rule, and then the derivative of negative 9x would give us minus 9, and then the derivative of 2 would drop to 0. So in parentheses here, my 10x minus 9 is representing that g prime, or the derivative of the inside function. The whole thing is in parentheses because I'm multiplying it to the f prime of g of x piece. Let's look at another example. So here we want to find f prime, where f of x is 10x minus x cubed plus 7x to the 5th, all to the 13th power. What is our outside function? Our outside function here is going to be this 13th power that we have as our exponent. So we're going to start by taking the derivative of the 13th power using the power rule. So let's start by labeling what we're finding. So we're asked to find f prime of x, our derivative of f. We start by taking the derivative of the outside. So to take the derivative of something to the 13th power, the 13th power would come down. I would end up with something then to now the 12th power by subtracting 1 using the power rule. Now in the chain rule, it says to keep the inside function the same. So our 10x minus x cubed plus 7x to the 5th all stays the same. So I did the derivative of the outside, kept the inside the same, times we now want to take the derivative of the inside. So to take the derivative of the inside, derivative of 10x would be 10, minus derivative of x cubed would be 3x squared, plus the derivative of 7x to the 5th would give us 35. Make sure I have enough space. 35x to the fourth. And all of that is in parentheses because that is representing, again, our g prime, or the derivative of the inside function. Let's look at some more examples. So here, we want to find dy over dx when y is x to the 15th plus 2x to the 6th minus 25, and all of that is being raised to the 11/2 power. Why don't you guys pause the video here and decide what your inside function is, as well as what your outside function is. So in this example, our inside function, if I start with that piece first, would be the x to the 15th plus 2x to the 6th minus 25. That is all being raised to our exponent here of 11/2, which would be the outside function. So when we want to take the derivative of this, we're asked to find dy over dx, our derivative of y with respect to x. When we do the chain rule, we start with the derivative of the outside function. To take the derivative of the outside function, I'd use the power rule, so the 11/2 would come down as our coefficient in front. I'm going to get something all raised to now the 9/2 power by doing 11/2 minus 1, which in order to get a common denominator, I'd have 11/2 minus 2/2, which would give me 9/2. So I've taken the derivative of the outside, that's representing our f prime, back in that general formula up above. I now need to keep the inside function the same, so our g of x, our inside function here, the x to the 15th plus 2x to the 6th minus 25 would stay all the same, times I now need to multiply by the derivative of the inside. To do the derivative of the inside, I'd power rule that, so I'd get 15x to the 14th plus 12x to the 5th, and then the derivative of 25 would drop to 0. So all in parentheses there, I have my derivative of the inside. So again, in blue here, I have my f prime, or the derivative of the outside function. In red, I've kept the inside function the same. And then times, in purple, all in parentheses, I have the derivative of the inside. Now, as you can see, since we're still working with algebraic functions, the power rule is still coming into play with all of these, but we're ultimately doing a chain rule first with power rules for each piece of these overall. Let's look at some more examples. So here we have g of x is the square root of 7x cubed minus 8x squared plus 9x, and we want to find g prime of x. Well, this one looks a little bit different. I don't have an outside power like we did above with the 11/2, but if I recall, the square root is the same thing as the 1/2 power. So I'm going to first take the step of rewriting the original function, so this is still my original problem g, and instead of writing it as the square root, I'm going to write everything inside that radical, all of that to the 1/2 power, since the square root is the same thing as the 1/2 power. Now from here, it's set up similar to examples we've seen up above, and I can apply that chain rule directly. Why don't you guys pause the video here and decide what your inside function is and what your outside function is, and then we'll check it. Our inside function here would be the 7x cubed minus 8x squared plus 9x, and our outside function would be that square root, or that 1/2 power overall. Why don't you guys apply the chain rule and find our derivative in example 4 on your own first? Okay, let's check this together. So to take the derivative using the chain rule, I start by taking the derivative of the outside function. To differentiate something to the 1/2 power, I'm using the power rule, so the 1/2 power is coming down, and I'm going to get something again, all to now the negative 1/2 power, by doing 1/2 minus 1 using the power rule, which would give us negative 1/2. Now in the chain rule, the next thing it says is to keep the inside function the same. So the 7x cubed minus 8x squared plus 9x all stays the same, times I then need to multiply by the derivative of the inside function. Now to differentiate the inside function, I would take the derivative of 7x cubed, which would give me 21x squared, minus derivative of 8x squared would be 16x, and then plus 9 for the derivative of the 9x. And that whole thing right there would be our derivative. Now in this case, we do have a negative exponent, so I can do a little bit of simplification by moving the negative exponent piece down to the denominator. So all of the 7x cubed piece would go down to the denominator. I also have a 2 down in my denominator from the 1/2, so don't think I have enough space down there, so I'm going to write it off to the side over here, but I'm going to get In one fraction, our 2 would be in our denominator. Now all of this to the 1/2 power, I could also rewrite as the square root in the denominator. So I had the square root of 7x cubed minus 8x squared plus 9x. And then in our numerator, I have our derivative of the inside, which would be the 21x squared minus 16x plus 9. And we want to make sure we are familiar with, again, rewriting those negative exponents back in the denominator. So all of this to the negative 1/2 power would become to the positive 1/2 power in the denominator. And then the 1/2 power is the same thing as the square root. Because if we were to have multiple choice question, more than likely it would be rewritten without negative exponents. Okay, let's look at one last example. So here we have y equals now the cube root of 80 minus x to the 5th plus x to the 10th, and we're asked to find our derivative. Well, in this one, what do you guys think our outside function is, and what do you guys think the inside function is? So in this example, our outside function is this cube root, and our inside function is the 80 minus x to the 5th plus x to the 10th. The first thing that might be helpful to do is to just rewrite this original problem. So I'm still going to call this y, but instead of writing it as the cube root, I can write all of that to the 1/3 power, which will be a little bit easier to recognize when I want to go take a derivative there and use the power rule for the exponent of 1/3. So let's take that derivative. So we're asked to find dy over dx, so I'll use that notation. And I've got to start with the derivative of the outside function. Our outside function here would be the 1/3. And to take the derivative of that, the 1/3 power would come down. I'd keep the inside function the same, so I'll rewrite that in a second. But our new exponent would be 1/3 minus 1, which would give us negative 2/3. So our new exponent here will be to the negative 2/3 power. So I've done the derivative of the outside. Now I need to rewrite the inside function the same. So 80 minus x to the 5th plus x to the 10th times, I still need to take the derivative of the inside. So all of this now, when I differentiate it, the 80 will drop to 0. Derivative of negative x to the 5th would be negative 5x to the 4th, plus our derivative then of x to the 10th would be 10x to the 9th. Both of those terms are in parentheses because it's all being multiplied to the first part of our derivative there. And just like in the last example, we can do a little bit of rewriting this to get rid of the negative exponent. So if I were to rewrite this, I'd end up with the 3 in the denominator, since I do have the 1/3 coefficient. I'd get the 80 minus x to the 5th plus x to the 10th. All of that would now be to the positive 2/3 power. Since I've moved that piece down to the denominator, the exponent becomes positive. And in our numerator, I have negative 5x to the 4th plus 10x to the 9th. And another way I could rewrite this 2/3 power would be the cube root of all of that squared if I would prefer. So I can also write that out so we can see what that would look like in case that happens to be the option on a multiple choice instead. So the numerator is still the same, and then I'd get 3 times the cube root, and then in parentheses, this 80 minus x to the 5th plus x to the 10th. All of that is being squared, which is coming from the 2 in the exponent, and then the cube root is coming from the 3 in the denominator. And I just need to close the parentheses, so all of that is times the 3 there as well. So the chain rule here we just saw with algebraic functions, but again, once we start incorporating trig functions, exponentials, and logs, the chain rule is pretty much going to be in every single derivative that we take because we always have a composition of functions overall. And we've secretly been doing this the whole time, so I want to go back and show kind of a basic example up here next to this. So if I just take the function, let's say y equals x squared. We've been really secretly doing the chain rule all along. Here our outside function is 2, and we know using the power rule, if I want to take the derivative of something to the second power, call it y prime here, the 2 would come down. I'd then get something to now the first power by subtracting 1. Now we were always just keeping that as x, because in the chain rule we do keep the inside function the same here, and x would be our inside function. But then I have to multiply by the derivative of the inside. Well, our derivative of x would just be 1. And we have been doing this all along without doing it kind of the long way, because in this case, this would just be equal to 2x, which is identically what we get just by using the power rule. But as problems get more complicated now, and instead of just having like x to the second, if I have something like x squared minus 5x plus 2 all to the second, now it becomes necessary to use the chain rule because the inside piece here, that inside base that's being raised to the second, got much more complicated than when we just had x squared overall. But we've been using this idea all along by taking the derivative of the outside, using that power rule, keeping the inside function the same, then times the derivative of the inside. And we're going to get lots more practice using the chain rule over the next couple classes.